Students, welcome to the next section, properties of locally connected spaces. So in this session I would like to prove that locally connectedness is a divisible property. What is a divisible property? A topological property is said to be divisible if a space has the property, so does every quotient space of it. Okay, so to prove locally connectedness is a divisible property, I need to prove that every quotient space of a locally connected space is locally connected. Locally connected space is locally connected. Actually, it is a proposition. Quotient space of a locally connected space is locally connected. Okay, how will you prove this? So, let X be a locally connected space. Locally connected space. Let X be a locally connected space. And let F from X to Y be a quotient map. When F is a quotient map, then Y is a quotient space. Therefore, Y is a quotient space. Quotient space of X. We have to prove that Y is locally connected. Okay. And to prove a space is locally connected, I am going to use one equivalent property of locally connectedness. To prove Y is locally connected, I am going to prove that Y has the property that every component of open subsets of Y are open in X. To prove this, we prove component of open subsets of X are open in X. We prove open subsets of Y. We prove component of open subsets of Y are open in Y. Okay. So in order to prove Y is locally connected, we need only prove this statement because they are equivalent. They are equivalent statements. Okay. So we want to prove component of open subsets of Y are open in Y. So I take let V be an open subset of Y. Let V be an open subset of Y and C be a component of V. What is a component? Component is nothing but maximal connected subset. Okay. What are components? Components are maximal connected subsets. Okay. And C be a connected subset which contains V. V need not be connected. Okay. So C be the component of V. We need to prove that C is open. Our claim is C is open in Y. This is we need to prove. Okay. Since V is open in Y, we can use the idea of quotient map. What is a quotient? We assume that F is a quotient map. Since F is a quotient map, which makes we have the topology on Y which makes F continuous, right? F is a quotient map means Y is the quotient space. Y is the quotient space means Y has the quotient topology. What is the quotient topology? It is the topology for making F continuous. It is the strongest topology making F continuous, right? So since V is open in Y and F is a quotient map, F must be continuous. Therefore, F inverse of V F is continuous means inverse image of open set is open. Therefore, its inverse image F inverse of V is open in X. Open in X. Which is an if and only if condition, right? So when V is open in Y, if and only if F inverse of V is open in X, because F is a quotient map or Y has quotient topology. So to make C is open in Y, we are using the reverse technique. Since to prove C is open in Y, we need only prove that F inverse of C is open in X. Okay. Similarly, since F is a quotient map, C is open in Y if and only if F inverse of C is open in X. So to prove C is open in Y, we need only prove that F inverse of C is open in X. Okay. So we prove F inverse of C is open in capital X. So to prove F inverse of C is open in capital X, we prove F inverse of C is a union of some components of F inverse of V. To prove this, we prove F inverse of C is a union of some components of F inverse of V, because F inverse of V are open. Okay, when a set is open, its components are also open, then union of open sets will be open, so does F inverse of C will be open. So to prove F inverse of C is open, we are going to prove F inverse of C can be written union of components of F inverse of V. Since F is a quotient map, we have F inverse of V is open in X. Then if you consider the components of F inverse of V, that will be open. Then union of open sets will be open. So using that idea, I am going to prove F inverse of C is a union of some components of F inverse of V. This is we are going to prove now. So for that, let I take a point, let X belongs to F inverse of C. Okay. Since C is contained in V, because C is a C is a component of V. Okay, C is a component of V. Therefore, F inverse of C will be contained in F inverse of V, right? So which implies X belongs to F inverse of V. Whenever X belongs to F inverse of C, that will be belongs to F inverse of V. Okay. Now let D be the component of F inverse of V containing X. Okay. Now I take what is F inverse of V, which is just an open set. Okay. So that need not be connected. So I consider let D be the component of F inverse of V. Okay. Containing the point X. What is here F inverse of V? F inverse of V is a subset of, which is an open subset of our capital X. Okay. And F inverse of C is a subset contained in, this is F inverse of C. We have a point X belongs to F inverse of C. Okay. Then X is also belongs to F inverse of V, because F inverse of C is contained in F inverse of V. Now, this F inverse of V need not be a connected set. So, F inverse of V may have more than one components. Therefore, you can consider a component of F inverse of V which is containing X. So, I take this is a component of F inverse of C. This is our D. D is a component of F inverse of V which containing the point X. Okay. Now, we have D is a connected subset of F inverse of V, because every components are connected, right? Which implies D is connected in capital X. So, D is a connected subset of capital X. What is F? F is a quotient map. In particular, it is continuous. So since f is continuous, comma, I can say that f of d is connected because connectedness is a property which is preserved under continuity. So continuous image of connector set will be connected. So since d is connected, f of d will be connected. Okay. Also, since d is a component of f inverse of v, d will be contained in f inverse of v. So which implies f of d is always contained in v, right? F of d is contained in v. Okay. Also, and what is actually f of d intersection c? Which is, I can say that it is clearly non-empty because we have the point x belongs to f inverse of c, right? X belongs to f inverse of c, which implies x belongs to f inverse of v. We have this. Okay, so x belongs to f inverse of v means f of x belongs to v, and f of x belongs to v. Yeah, so we have x belongs to f inverse of c. Okay, sorry, x belongs to f inverse of c. Therefore, f of x is a point belongs to c, right? And what is d? D is a component of f inverse of v containing the point x. So I can say that x is always belongs to d. Therefore, f of x will be belongs to f of d. Right? So f of x is a point belongs to c and f of x is a point belongs to f of d. Therefore, f of x is a point belongs to both c and f of d. Therefore, f of d intersection c will be non-empty. So which implies f of d will be contained in c. So which implies d will be contained in f inverse of c. So what you get now? What is d? D is a component of f inverse of v containing the point x. Then d is contained in f inverse of c. Right? Which implies what if you take any component of f inverse of v, that will be contained in f inverse of c. So that f inverse of c is nothing but f inverse of c is the union of components of f inverse of v. So which implies f inverse of c is open. Why? Since union of open sets is open. Union of open sets is open. And components are open. Components of open sets are open. Okay. So using that idea, we get f inverse of c is open. So which implies whenever f inverse of c is open, f is a quotient map, corresponding c will be open in y, which implies c is open in y. What is c? Component of, what is c? C is the component of v, which implies component of v is open. So component of every open set is open means that space is locally connected, which implies y is locally connected. So locally connectedness is a divisible property, or quotient space of a locally connected space is always locally connected will be proved.